with a few problems to work through. The first thing you're going to do is just play with bidding random variables to get a feel for them. So, and we're going to just start at the beginning and bin uniform random variables. So in MATLAB, like we mentioned yesterday, this function rand will generate uniform random variables. So I'm going to, if I were just to say generate rand of 1,000, it would do 1,000 by 1,000 matrix. So I just want 1,000 total, so I'll do 1,000 by 1. And then really, and actually I should have taken these out for the file I set omit, but there's a bunch of these break commands in. You can just take those out, but I just wanted to go through this slowly. So I'll leave them so the program doesn't finish. Oops, and we don't need to see that one yet. Okay, so this doesn't look very interesting, really. And let's see, what are we plotting here? So remember, I mean, we draw these functions that are how they're supposed to be distributed, but really we're just looking for numbers on the real line, right? So for uniform random variables from 0 to 1, I'm looking for numbers on the real line. Here I'm plotting numbers on the real line. Those are the locations of the numbers, and the put them on the real line, I'm multiplying by 0. All right, so when we're zoomed out, this doesn't look very interesting. It almost looks, well, it looks uniform, right? But it almost looks solid, but it's not solid, right? If we zoom in, we can see that it's sort of filling in the space, right? And if I move this up to 10,000 or 100,000 or a million, it would fill in the space even more. Okay, so that's our, that's one way to see them. And actually in 2 dimensions, that's not a bad way to look at things. But in 1 dimension, it's kind of hard to see what's going on. So we've seen that figure, so we'll hide it. And now we'll bin these random variables. So I guess I could show you this first. So my random variables were called x. So I could, MATLAB has a built-in histogram function, right? But when you use a MATLAB function, there's a little bit of magic, and this isn't a very hard function. So we're going to write our own histogram function, or it's already written, so you'll just use it and modify it. We want to be able to manipulate it some. So that's there, of course. If you want to learn more about it, there's always help. So here's what we're going to do. I'm going to break this up into into 20 bins. This is the sort of thing you can decide on for your problem, how you want to see it. And that's something that there's not a right answer for. It's something you play with. Then this is a uniform 0, 1, so our domain goes from 0 to 1. If you have an infinite domain, you're going to have to choose some cutoff, right? So that depends on the problem. That depends on the problem you're thinking about. This d bin is just the width of our bin. Okay, and then I want to put this grid on, right? I want to put this grid on, and so I use this command. I use this command called linspace for linear space that just builds a grid. Right, so this linspace command is going to start at 0, end at 1, and put 20 marks. Actually, I need 21, right, if I want to define 20 units. Right, so that's why I have the 1. Then, for plotting purposes, I need this x bin c. So this is just all my names, right? So that's for x bin centers. So really, then I want to pick off the centers of these bins for when I plot. Okay. And to do that, right, what do? Well, I really just want to add half of a bin space to each of these guys, except for the last one. So that's all we have here. And then we're going to fill in, actually when we do the binning, we'll fill in the values, how many random variables fell in each of these guys. So that'll be our bin values. This is one thing in MATLAB, so you guys all seem like pretty good programmers, but if you're new to MATLAB, 20 is a pretty small vector, but if you have a very large vector, and you don't what's called pre-allocate it, MATLAB will be slow because it sort of does this dumb thing in memory where it says it's going to build this vector one at a time as I go through my loop, and it's putting chunks in here and here and here in memory. Right, so you want one big chunk in memory together, so you just define it first with zeros typically. Okay, I actually don't think I need this, but this function sorts my random variables. So I don't think I need it for what I wrote, but that's okay. I guess I don't really need the break there because there's not a whole lot to show you. Okay, this is where the binning goes on. And again, this is, probably not as efficient as if we just ask MATLAB to do it itself, but it's not bad. It doesn't take too long. So basically what we're looking for, we really want to count how many random variables fall in each of these bins. Right? So I go through the number of bins, and my XORT are the random variables sorted. And I don't really care about their values so much, not what we're doing here. I care about which of those random variables those indices belong to. Right, so it's maybe, for the first bin, maybe it's the first 48. Right, so this would be index 1 through 48. And then we'll go through the loop, so we'll move one bin over and then count them. So this find command in MATLAB is really useful. Useful for all sorts of things. So that's a good one to do help on. Not just in this context, it's often useful, because often what you're interested in isn't the value, but the index associated with the value you want, so you can go get it, right? All right, and then, again, we're not actually interested that it's 1 through 48. We're interested in the number. So I'm just going to find the length of that vector. Right? So this is a vector of indices. I really want to know the length of it. I want to know how many random variables there are. So I'm going to call that bin values, and I'm going to go on to the next bin and repeat. Okay, so we'll look at this figure. Did I not take that off? Oh, did I not save? I did not save. Save. Okay, so here's our binning. So does this look as good as last time? To you? I mean, there's not a right or wrong answer. You just tell me yes or no. It's objective, or it's subjective, right? There's not a right answer. Does this look as good as the last time? No, so I don't think it looks as good. And there's only one difference, right? There's only one difference in that we used more bins, right? And there's no right answer to the number of bins you should use for the number of things you're binning, right? You just want to get a sense of what's going on. So this is a number you can play with, right? We could change this to 10 bins, to 100 bins, whatever we like. I keep wanting to use the mouse that controls this instead of my laptop. Let's see. One other thing I want to look at. So we have these, let me print them to the screen here. You have a question?
You are giving random numbers.
Uniform random numbers.
That should be Gaussian.
Uniform random numbers. All right, so we talked about, so the very simplest distribution that we saw yesterday was we're just looking from numbers from 0 to 1, and their probabilities are equal. I can't draw straight lines, so ignore that, but there should be a straight line equal. Right? So this is what we need. This is sort of the backbone that we need to be able to sample uniform random variables. Gaussian's next. Right? So we work our way up. So that's the probability distribution, and actually this histogram, right, it sort of looks like the probability distribution. It should, right? If you're doing things correctly, it should look flat. There's one other for uniform random variables. what do we call that? Bin vals. Okay, so here are the number in each of our bin. We're only seeing the last 10 or so. But if I have 1,000 samples I'm drawing, if I add up all the numbers in the bin, what should I get? And all of the bins. So it is this easy, right? It's this easy of a question. What should I get? So I'm counting how many of each of my samples are in each bin. If I add up the number in each of the bins, so let's say get the total number of samples, how many should that be? If I started with 1,000? 1,000, right? So these are the sorts of checks you can do though, right? So I have this variable called bin vals that's storing the number in each bin. So if I sum bin vals, it should be 1,000. Okay. So now, and let me actually bump up the number of samples here. So we'll do 100,000. And this histogram is really sort of an approximation for a PDF, right? But we have to normalize it, right? So I sum this is going to sum to 1,000. For a PDF, I want it to sum to 1. So I'm gonna do this. So I've divided by my thing that sums to 1,000 by 1,000, so it'll sum to 1. And now we'll plot it. And we'll also plot the actual PDF. So the actual PDF, right, is just, it's 1 from 0 to 1. So we'll plot our PDF and the actual PDF. And I think actually I need to maybe take out another break. Oh no, that looks okay. Let's see. There should be a figure 2 somewhere. Can't quite see. Right, so this is our PDF approximation, which isn't at 1. And the actual one that I drew up there is at 1, but you can't see it because MATLAB cut off the graph there. So let's change that. Oh, and I don't want figure properties, I want access properties. So let's go to 1.1. Come on. Oh, I changed the X, right? I should change the Y. So it did what I wanted, or it did what I told it to do, right? This is the problem with programming. You think, that's not doing it, right? But it's doing what I told it to do. I just didn't do what I thought I told it to do. It's often the problem. Okay. So here's our PDF and there's an actual PDF. So what's the problem here? There's a problem, right? Well, clearly there's a problem because they should be the same, or close to the same. Close to the same. Any ideas? Right, actually that's interesting. So let's change the number of bins. So you think I should make it bigger or smaller? Smaller. So 10? Well, it moved it. But it's still not right, is it? Yeah. But that's interesting, right? It's somehow related to the bins, this problem we're seeing. Right? So let's think about the other things we know about PDFs. If this was a PDF, it's not, right? Because this is the PDF. So actually, so if this rectangle, right, I mean, we can all see this big rectangle with the black top clearly integrates to 1. Agreed? Right? Your 6-year-old nephew would know that, right? A 1 by 1 square has area 1. So clearly, neither of these guys have area 1. And when I changed the number of bins, it moved up a little. So how would we check? Right, so we want to see maybe what the integral of that is. Right, and my sort of quick and dirty way to do the integral would be to sum my bin vals times the width of the bins. Well, but the bin vals has about, right, or to sum our PDF. That's what we called this thing. We called it our PDF. And our PDF sums to a 10th. Right, so what we plotted there, we have to scale it by the width of our bin, right? That number shouldn't change as I change my bin size. So really our PDF, we were missing a term. And in the code you get, it's missing, so you're going to want to fix it. Let's see, where did it go? Our PDF shouldn't just be scaled by the number of samples, but by the width of the bins. Okay, now, let's see, now this should work, maybe. That doesn't look very good either. Or does it? Looks kind of bad, I think. How can I make it look better? How can I make it look better without rerunning the program or changing anything in the program? The axis, look at how small those values on the axis are. Right? So when you're plotting something, you're like, wow, that looks strange. You have to think about what you're plotting and what you're seeing. Right? Because sometimes the window MATLAB gives you isn't the window you would have picked. Right? So let's change this window. So instead of going from 0.98 to 1.02, we'll go from 0 to 1.5. Now that doesn't look bad, right? It's not perfect. It's not perfect because we're sampling random variables and there's inherently some error there. There are theorems, and then we'll talk about some tomorrow, whenever the next time I talk is, about if you increase n more and more and more and more, this thing's going to flatten out until you can't notice the difference. Right? And this is the game we play where how many n do we have time to actually deal with? Right? And how good are you, how okay are you with not being perfect? Right? This is always the balance. We had infinite number of samples, we could do anything we liked. Right? Okay, any questions at this point? Comments? Okay. So you will have this script. And you're always going to want to compare these to the actual PDF. And if some of you aren't familiar or too familiar with plotting in MATLAB, I wrote in the PDFs for the distributions you're going to want to think about. And there's one thing in particular I want to emphasize. And MATLAB, well, I think probably what you saw yesterday is if you take a product of vectors and matrices, it automatically does the linear algebra vector matrix product. I mean, in star is is how we take a product of anything. But if I want to take a scalar product, right? I have a vector. I want to multiply each element by the corresponding element in another vector. I need this dot. Right? So if I want to square each element individually, I need a dot. If I want to multiply or divide, I need a dot. Right? So that's just something that can trip you up if you don't know it. So those are all sort of ready to go when you're ready to use them. All right, so let's talk about the worksheet. I need to zoom in some. Is that enough? One more? That's enough, okay. Okay, so the first thing you're going to do, the first order of business is change 0, 1 to some other interval. All right, change 0, 1 to some other interval. And we can, the transformation isn't too hard. Oh, thank you, thank you, thank you. I do need an eraser though, that was part of the problem.
Just check if you got the 5 names.
Huh?
5 names.
If what?
The 5 names which I...
Oh, up here. Oh, I erased one of the names. Okay, so let me write that again. Let me erase this. So we have x from uniform 0, 1. How do I transform this? So if I give you this number, how do you transform it to be, say, z, or let's say y? I should just hold on to the eraser maybe. Y from uniform some number a to some other number b. We'll always think of a as b being bigger than a. So this goes from 0 to 1. Right? Smallest number is 0, biggest number is 1. So what's the first thing I'm going to do to it? How do I take 0 up to a? Plus add a. Okay. How do I end at b? So maybe I'll leave this up for you guys to work out. I mean, it's not too tricky, but it's something you're going to need to do. Right? You're going to need to do a linear transformation like this. Right? And if someone wants to tell me the answer, I'll write it down. Otherwise, it's your job. Okay. So the next thing we're going to do is we're going to repeat this process of binning now with Gaussian random variables. So now we'll get that shape. Right? So the first thing we'll do, so rand, R-A-N-D, gives you uniform random variables in MATLAB. Rand normal, gives you normal or Gaussian random variables. Right? So and it gives you mean 0, variance 1. Right? That's what MATLAB gives you. So we're going to repeat these sort of ideas of playing with the script to bin and to make an approximate PDF, change the number of samples, change the width of the bins. And here I've written down the transformation for you. Right? If we have if we have z as a standard normal, which is n0, 1, and we actually want a sample that comes with mean mu and variance sigma squared, then this is a transformation. Right? So basically we add the mean and we scale our random variable by the standard deviation. And here, right, I set up this linear space, my bins, from 0 to 1. For this, you're going to want to change the endpoints, right, that makes sense in your problem. And it's not, especially with the playing a script like this, it's not like you have to get it right the first time. Try it, plot it. It looks silly, then you know you need to change your numbers. Okay, any questions on this first problem? Okay, so this script I just worked with will be posted. Remember, you want to take out the breaks and you want to divide by the D bin to scale the PDF correctly, to scale the approximate PDF correctly. Okay. So now we're going to go through so we sort of talked about 3 things yesterday, and we're sort of going in order. We talked about random variables, and some ideas of probability. We talked about this integrate and invert method. So now we're going to do it. And first we're going to do it for an exponential distribution. So here's an exponential distribution, Q of y. The h is just there sort of in place of for y greater than 0. Right, so h is this function that's 1 if y is positive, 0 if y is negative. We don't need to define it at 0, so it doesn't matter. Right now we can go through this process. We'll go through it since it's written down already. But really, we have the PDF, the CDF, the cumulative distribution function from the slide yesterday. Did you put those slides up on it?
Yes.
Okay, so those slides yesterday are posted. So you can look at the formula, which we get to down here. Right, but we could have gotten to that by integrating. Right, so we're going to integrate this thing. This h function, which is known as the Heaviside function, basically just says, well, it's 0 if y is beneath 0, so it just changes the limit of integration first, and then we can ignore it. So we're going to integrate this. This is, the first integral you learn, or the second integral you learn. And this thing has to equal x, right? And this thing is our function g inverse, right? That's why we did the integral, because we wanted to find this function g inverse. But we wanted more. We wanted g, right? Because remember, what we wanted is we wanted a function that if I were to plug a uniform random variable in here, I get an exponential random variable out. Right? That was the goal. So in cases where we can do it, we need the CDF, or I need to integrate so I can get the CDF, and then do the inversion. Right? So here are just the steps to the inversion. Right, so I have x is 1 minus the exponential of negative lambda y, a few steps of algebra, and we get this. Okay, so here's some questions. If these seem really obvious, you should tell me the answers now. If not, I want you to think about them. So y up here, right? Y should be distributed according to that function, according to this exponential, right? So generically, this exponential distribution looks like that. And there's a negative sign in my formula, right? There's a negative sign in my formula, which is distressing, because I should be getting variables out here. None of those are negative, right? So should g be negative? Is g negative? Right? And these are the sorts of things when you're doing a calculation you need to think about, right? The negative sign makes me nervous because I know this shouldn't be negative. It's not, but there's something you want to think about. Another thing, remember what we're doing, we're sticking a 0, 1 uniform random variable into g. So this is the formula we get, and I claim that we could have written down that. The same formula with 1 minus x replaced by x. Right, and I want you to think about why that's legitimate. Any thoughts on those questions? Okay, so this uniform random variable is symmetric, right? If I have something distributed uniformly between 0 and 1, say it's right here, then if I subtract that number from 1, it goes over here. Still a random variable, still the same distribution. You could show that more rigorously, but the idea is the same. Okay, so now actually it's maybe easier to think about the first question if we look in this case. Why is that not negative? It's not negative. Huh? X is less than 1, right? So of course we need that negative sign there. Right, but these are always the sorts of things you should be thinking about. Okay. So now the second script you have, let's see if it's up here, is to do this. And I didn't really need to write this for you. You could have written this, right? I mean, this is, nothing to it. I have the number of samples I want. I generate that many uniform random numbers. Lambda is a number you can choose, right? Lambda is just going to tell you how high up you start, right? And how quickly down your tail goes. Because you always need that area between the PDF and and the axis to be 1. And then I have my transformation. So once you have the transformation, there's nothing to it. Right? The transformation is the work. The work is pencil and paper here. Okay, but we can run that. So what was that called again? Expo. So it's exponential random number generator. Oh, log. Okay. So MATLAB doesn't have that command. It has this command for log, for natural log. If you want a log base 10, you put a 10 after that. So this is natural log. Log base 10 would look like that. If you want to log with another base, you can either do the transformation maybe you remember, or you can ask MATLAB how to do it, but it'll do it for you. All right. Okay, so now we have these random variables. I call them y. And I'll just do a hist of those. Well, that looks reasonable, right? The histogram doesn't scale it, right? So I'm not really looking at PDF, but the shape is like the PDF, right? The shape looks like the shape I drew. So that's pretty reasonable. So the next part of your assignment is to play with these exponential random variables and bin them yourselves. Right? And there's a number of ways you could go about this, but maybe the easiest way is to just go ahead and generate them and use this save command, which will save my random variables y in the parameter lambda into this function, or into this file called exponential random variables. Right? And there's something called a .mat file. That's MATLAB's data type, which is very unfriendly if you want to use it with some other program. So don't use it unless you're going to use it with MATLAB. But now if I save those and I want to, so I'll show you just quickly. Okay, so now those are saved. So I'm going to clear all. I don't have any y, I don't have any lambda. And now use that same command load. Right, so now I'm going to load that file I just made called exp_rvs. Okay, now my random variables are there. Lambda's there. Right, so as you could save those, you could then when you want to run the bin plot, just load them, right, and plot those. Okay, questions? Comments? Alrighty. Okay, so the next part of the project is to go through the same process we just went through exponential random variables for a Cauchy distribution. Right? So you can either look up the CDF, you don't have to do the integral by hand, or you can try the integral by hand. It's probably going to be worth your time to try it. You're going to, again, want to bin this, so you can use your script to bin it and to get an approximate PDF. Here you need to be a little bit careful when you're binning. If you're not careful, things are going to look really strange. And that's because you're going to end up with samples way out in the tails. Remember, this had heavy tails. There's still a high probability that you would sample far away from sort of where the mode is. So there you're going to, there are a number of ways you could deal with this, right? Because all you're doing is plotting. You're not coming up with something analytical. You're just plotting. You can define your bins, to be around your mode in some domain, and then you can basically, in your binning code, you say anything that's smaller than the first bin, just put in the first bin. Anything that's larger than the endpoint of the last bin, just put in the last bin. Right? So those end bins are going to stack up a little bit, but it's going to account for the tails. Otherwise, really strange things will happen. Okay, questions? All right. The last problem is to do rejection sampling. So now our goal is to generate random variables from this gamma distribution. So here's the definition for a gamma distribution. We're going to use the n of 5, or you could use whatever you like, but 5 is a fine number. Gamma is a function, so it's going to give you a number. I think the gamma for n is 5 is 24 or 28, something like that. So basically I have x to some high power times a decaying exponential. Right, so our distribution does this sort of thing. And it's only defined for positive x. So we're going to use our Lorentz distribution to be the one we sample from in rejection sampling. But now, right, my Lorentz distribution integrated to 1, now I need to use something that doesn't. I only need to use something that's actually bigger than this gamma distribution. So you're going to want to pick some values of C naught, X naught, and A naught. Those are all just parameters. You pick them. Pick a few, plot them. It doesn't look like it works. Pick some others, right? And change one at a time to see what it does to the function. Right. So once you have a C naught, X naught, and A naught, then you get your function to be. You get your function here, this sort of Lorentz-like or Cauchy-like function. To be above Q, to be above the distribution we're interested in, then you can use it in your rejection sampling. Okay, so that's the first piece of the battle, which is just plotting, right? All that is plotting to pick those numbers. All right, let's see. Next, I need to know what this integral is. Right? I need to know what the area under that curve is. And what's going to really look different, so we're using the same function as the one you just integrated and inverted, right? So this is going to look really similar, except I truncated this because I only wanted random variables bigger than 0. So I've also truncated this distribution, which changes the limit of integration, right? So it's going to change your CDF. So you have to be a little bit careful to get the details right, but basically it's going to look like what you just did. Right, so the first thing you want to do is integrate it all the way to infinity. You can do it by hand. You do it numerically, I don't care. I mean, I just want you to get the number. Right, I just want you to get an estimate for A. If you do it numerically, you have to be careful though, because this function keeps going and it's heavy. Right, so there's a lot of contribution. You can't just go up to 10. You can't go from 0. You can't call 10 infinity. Right, this is, you know, I teach numerical analysis a lot, and then when I teach calculus, I think, well, infinity, you know, 100, 1,000, a million, right? It's some big number, right? And effectively, if you want to integrate something numerically, that's fine. You have to be careful with this function, though, because there's still stuff out there that you're not accounting for if you don't go out far enough. So integrate exactly, or choose your approximation for infinity to be quite big if you want to do that numerically. Okay, so we integrated to get the this constant, the area under that curve, and then we also need the integral, the indefinite integral, so from 0 up to x, to invert it. So we do that integral, we invert it, we get something that looks a lot like our last problem, a little bit different. And again, your bottom limit of integration changed. Okay, and here's the algorithm for rejection sampling. And it's pretty explicit, right? This is pretty explicit. So in some ways, it doesn't really matter if you didn't understand me yesterday. If you go through this step by step, it should work. Right? So I'll talk through it and try to relate it. And my discussion about it, right? That's in those notes that are posted, so you can look at that too. But what's the process, right? So we draw this uniform random variable from 0 to A. You already know how to switch uniform random variables from whatever range you like. So now you go up to whatever number A you found. We call that uniform random variable Z. We have our transformation that we did by hand, right? By hand for the function we chose. And now I plug this number I have into that function. So I know the function G. That gives me some other random variable X. Now I take X and plug it into that Lorentz-like function, Cauchy-like function. plug it into this f, right? And I get some number out. And we'll call that number b. Then I take a uniform random variable from 0 to b. We'll call it y. Y, again, that's a number, we know it. I take the same x from step 2 and plug it into my distribution I'm interested in, q. And if y is bigger than q, we throw away x. If y is less than q, we keep x. We're going to repeat this process over and over again until we have however many samples we want. Right? We want 10,000 samples, 100,000 samples, whatever. We'll just keep doing it. We also want to keep track of, the only other things, we want to keep track of how many we're keeping and how many we're throwing away. And does anyone remember why we want to do that? If not, you can think about it. It's okay. You don't have to remember right now. But that's something, that's sort of a check, right? It's not proof that the algorithm works, or it actually might be in this case, but it's definitely a check that the algorithm works. If that ratio is correct, whatever correct is. Okay, questions? Comments? So I'm not sure, Amit, what you were thinking. So I guess you guys have an hour and 15 minutes just to work. I'll be around. I think Amit will be around, or not. I won't pin you here. And I don't know that you'll get through everything, and I'm not sure when we'll reconvene to talk about this. So I don't know after the lecture tonight or maybe during the questions tomorrow night. But at some point we'll reconvene, some point before tomorrow evening, to discuss this stuff. Right? And before... Okay. Well, maybe after Dave's talk, would that be better? But although I don't want you to work during Dave's talk. So that's the caveat, that you have to have the computers closed during Dave's talk. But that way there will be time and it won't be cutting into coffee or anything. Okay, yeah, I'm going to play it by ear, but certainly I'll be around. And normally with assignments, I don't care where you go in, but this assignment you kind of have to go in order, right? So it's kind of step by step. Otherwise you'll get ahead of yourself and you'll miss pieces you wanted to have. It can be bad. Yes. Yes.
The A that accuracy step was integral, which was.
I agree.
And if A is not accurate enough,
And even better to do it with the parameters in there, right? With not the numbers, right?
that's easy integral.
Yes. If you remember it, or you can certainly look it up.
Or just look it up on
Yeah.
Google from.
Yeah. But better to do by hand. And you're gonna need it. You're gonna need the antiderivative anyway, because that builds the function you're going to invert.
Even the definite integral, should we do it?
Yeah, yeah. Right, it's a...
For definite, 0 to infinity for sure. If it has a pi.
Right. You actually have to be careful. It is sensitive to getting the interval correct, the details correct.
Yeah, so I think that's why getting the constant A right.
Getting the A, but actually also on the indefinite case, when you plug into 0, you have to have that constant correct. Right? So you want to, if you don't do it, things will look strange. You'll get random variables in negative places. You'll get gaps. Yeah, so funny things will happen. If you see funny things happening, that interval is a place to look. Okay, and any of the PDFs that you should need are all commented out. I didn't test them, so if you get an error when it runs, you call me over and I'll fix it. But so you shouldn't have to spend too much time on just the plotting stuff. Okay, and these are up now? Yes, perfect. Okay. Am I done with this?